has what is called anomalous expansion of water at temperature below 4 degree centigrade. So water behaves just like any solvent. As it gets warmer, the density of water decreases, but that is okay only up to 4 degree centigrade. Beyond that, it starts getting lighter. So that's why you have ice floating on water. Normally, other solvents will, in the solid form, are not going to float on their solutions. So this is what is called the anomalous expansion of water, and you're familiar with it. But what are the implications of this, especially in temperate and Arctic regions? Arctic, Antarctic, all these regions. Okay, so the first thing that you probably know from ecology is that ice forms a blanket, it's 0 degrees, and the water below that is 4 degrees centigrade. And therefore, aquatic ecosystems continue to survive and thrive despite harsh winter conditions in temperate and the frigid latitudes. Okay, so despite all that, they are able to survive, and that is something that happens only in the temperate and um, colder regions. Now, there is another implication of this, and that is what is called thermal stratification. Now, thermal stratification happens in all cases. It happens in tropical water bodies, it happens in the oceans, it happens everywhere. Because after all, the density gradient, which is related to temperature, is going to happen everywhere. Whether you have a small bucket of water or whether you have the entire ocean, it doesn't matter. You will get a density gradient related to temperature. So let's see. Why is it not? Okay. Now here we have the aquatic water body. You know, we call the water column. So let us say you have the ability to see into the water and you're looking at it into the depth of the water. So this is what we call the water column. And this is the depth of the water. So this is at the top, you have the surface. So this is my 0 point. And there are two axes that are shown over here, temperature and dissolved oxygen. Now you also know one more thing about dissolved oxygen as well as temperature. You know that as the temperature goes down, the amount of oxygen dissolved in water will go up if it is clean and pure water. Okay, so please mute your mic. Whoever that is, please mute your mic. Okay, so as the temperature goes down, your DO level rises. Now, what happens in summer? In summer, the ambient temperature is rising. That will have an impact on the water temperature. So the water temperature will also rise. Now, if the water temperature is rising, the DO profile is going to, the DO concentration will go down. Okay. So temperature goes up, DO goes down. So DO concentration with depth is what we are looking at in this particular water column. Now, in lakes, we have 3 layers, and I'll just show you. Let's just look at these 3 layers. So the top layer is called the epilimnion, the one in the middle, which is often the smallest, thinnest layer, that is called the thermocline or the metalimnion, and the one below that is hypolimnion. Now, the depth and thickness of these layers is entirely dependent on the depth of the water body. And there are several other things that are related to these 3 layers. So this is one type of stratification that you can see, but there is another thing that needs to be kept in mind. And there are 2 words that I will use when I talk about what is happening over here. So that is the euphotic zone and the aphotic zone. So euphotic means, so epilimnion is the top part, and euphotic means that light is able to penetrate into water. So when light is able to, just one second. So the euphotic zone is where light is able to penetrate into water. Now, you know that the ability of light, we've already done this in the last class. The ability of light to penetrate into the water is dependent on the turbidity, it's dependent on the wavelengths of light, and it's dependent on the plankton or other suspended matter. So all those factors will depend, that will determine the depth of the euphotic zone. The remaining part of the water column is called aphotic. Aphotic means no light. So that is where the dark part begins. Now, algal growth and all of that will happen only at the top. And what is the algae doing? The algae is generating oxygen. Now, at the top, in the epilimnion, two things are happening. You are getting re-aeration at the surface because of mixing by wind and wave action. You are getting DO from two sources. One is equilibrium with the atmosphere. So if we assume the atmosphere is above the water, that is the major source of oxygen. And the secondary source of oxygen is photosynthetic organisms. Because light is available, because CO2 is present, they will grow over here. So you have algal cells growing over here, and they will contribute to the net dissolved oxygen in this layer. So this layer has a pretty high oxygen level. Then, depending, like I said, on the quality of water and the depth of the water column, there will be a point at which you will notice that there is a sudden and steep decrease in temperature. Now, this first layer, let's look at the red line, which is the temperature profile. So in the top layer, which is the epilimnion, we have mixing at the top. So because we have a mixed layer, this part has a more or less uniform temperature, very little change in temperature. Below that, where the water is not penetrating, where there is no, where the light, I keep saying water, where the light is not penetrating, and that will cause a steep decrease in the water temperature. So that is why it's called thermocline. Thermocline means steep incline. So the slope of the temperature profile is the steepest, and that's why it's called thermocline. So there's a sudden and steep drop in temperature. The depth can be as shallow as 1 meter or even as deep as 20 meters. It all depends on the water quality, because as long as light is penetrating into the depth of the water, the light is heat as well. So it's heating the water. So that is another reason why you have a fairly uniform profile here. And then as the temperature goes down, your DO levels, if the water is fairly good quality water, the DO level will start rising, for the simple reason that the DO saturation for low temperature is higher than the DO saturation for higher temperatures. So you get this interesting profile, and then comes the third layer. The third layer is generally, there may be exceptions, I'm not sure about that, but below in the third layer, this is the dark zone. In general, the hypolimnion is associated with the dark zone or the aphotic zone. And I don't think, even though I've written what I've written over here, I don't think it happens, because if there is light, there is heat. And as long as there is heat, the photosynthetic organisms will continue to grow, and the water will have a lot of DO and so on. So if there is light, photosynthesis will happen. If it is dark, no more photosynthesis. Photosynthesis means you need light. At this point, because there is no photosynthesis and there are two layers of water on top, so there's no equilibrium with the atmosphere either. This is the zone where the bacteria will start dominating. They are the ones that feed on dead, I shouldn't say dead. These are the bacteria that feed on organic matter. Now that organic matter can be dead algal and bacterial cells, or it can be vegetable matter. It can be anything. Bacteria will feed on anything. What do they require along with the organic matter? Along with the organic matter, they require dissolved oxygen. So this is the zone of DO depletion. There is very little. The only input of DO in this third layer is by diffusion from the top. There is no there is no other source of DO in this layer, unlike the top layer. Top layer, remember, has two sources, atmospheric oxygen and photosynthesis. Second layer, again, it's getting DO by diffusion. And the third layer has nothing else except whatever is left over from the top two layers. Okay, so that is the dark, cold region. This is the profile in summer. This is true for tropical lake systems throughout the year. This is like an unchanging, stable, what we call thermal stratification in tropical aquatic water bodies. So if you were to go and take a dive into any reservoir, any lake system over here, you will probably find this kind of temperature profile. And it's unlikely to change throughout the year. There may be small fluctuations, but because there is no sub-zero level ambient temperature. So tropical systems means there are that ambient temperature never falls below zero. So it's not going to change. But what happens in the temperate regions and in the colder regions? So here are two things that happen. Now, we've already seen the first one. Let's take a look at the next season. So after the end of summer, you have fall or autumn. It's called fall in the northern countries, and it's called autumn in our parts of the world. So let's take what happens. Let's take a look at what happens in the fall. Summer temperatures start decreasing. There comes a point. Let's say the ambient temperature comes down to 4 degrees. The water temperature comes down to 4 degrees, and you know that at 4 degrees the density is greatest. Okay, so suddenly when the layer of water at the top has the highest density and the other layers are also at the more or less at the same temperature, because you get a uniform temperature profile. So this is going to get completely turned over. There will be complete mixing, because this this profile, which was based on the temperature and the density gradient, so as the density gradient breaks up, so remember that we are now moving from low density to high density. So eventually there will be mixing and you will get a completely uniform temperature profile, and that is called turnover. So because of this fact that the density gradient has broken up, the entire thing, this whole thermal stratification, which is based on temperature and density, will break up and you get complete turning over of the water. So at this point, you will get a temperature profile that looks like this and a DO profile that changes, because whatever is at the top is in response to the ambient temperature. So that's why you can see the DO saturation is higher. So this point has gone higher, and as the temperature remains the same, but as you go deeper into the water column, the DO is being depleted by the bacteria and maybe even other higher organisms. So they're going to deplete the DO, and as you go deeper and deeper, if the water is not good quality water, then there is a possibility that the DO level can come down to zero. I have not shown zero. It can be zero, it can be higher than zero. Okay, that is the second season. Then we come to winter. What happens in winter? In winter, let's say the ambient temperature continues to drop. Eventually, a layer of ice will form at the top of the aquatic water body. Okay, so yeah, so here we have a layer of ice at the top. Now, this ice is lighter than water at 4 degrees centigrade, so it's going to float at the top. So you have this kind of 0 degree, and then everything below. Now, this ice is forming a blanket. So it's kind of like a trap. So the water below that ice is going to be uniformly at 4 degrees centigrade. And this is, like I said, what allows organisms higher and lower to survive throughout cold winters. It doesn't happen in tropical climates. It happens in sub-zero, where the temperature of water is either zero or below that. It happens only at that time. Then we come to the DO profile. So the DO profile will be more or less the same, but with a key difference. Now this water body is kind of closed. It's no longer an open system. Oxygen is no longer, because there is a blanket of ice at the top, it's no longer in equilibrium with the atmosphere. So whatever dissolved oxygen was there in the water is the only source of oxygen that has to last for the entire winter. So now if the winter is 2 months, that's okay. But if the winter is 6 months, if it is polluted, that DO is not going to last. So what happens very often is when winter changes to spring, when the ambient temperature starts rising, the ice thaws, and many times people have observed that the organisms, especially fish, they are found dead. And sometimes people panic and they think that, oh no, there must be something toxic inside the water. What was There may or may not be something toxic in the water, but what is definitely true is that the dissolved oxygen is completely gone. So, how will the fish survive? So, that is something that happens very often, that when winter is followed by spring, if the not river, lakes and reservoirs, if these standing water bodies have been polluted, then there is a significant loss of dissolved oxygen during winter. As long as the ice is there, that loss is not visible, but the moment the ice thaws, the loss becomes obvious. Okay, so this is what happens in temperate and frigid regions. In tropical lakes, like I said, there is no turning over. And the textbook, I don't, not in mine, but there are other textbooks that talk about the fact that this stable thermal stratification, which happens in tropical lakes, can lead to the formation of let's say explosions of methane gas have happened, explosions of CO2 have happened, even though CO2 is not flammable. And when I say explosion, it doesn't mean fires. What I mean is that there is like a huge bubble of this gas that forms, it rises, and the entire thing explodes in a massive expansion of the gas. And what it did in, I think this is CO2 expansion, that caused suffocation in several villages in Africa from a large lake. So Nios, I think, yeah. So this is described in the Masters and Ella textbook. So if you're interested, you can take a look at it. And it's there on the internet as well. So there can be all kinds of consequences to this thermal stratification, not just in temperate and frozen regions, but also in tropical regions. So a lot of people in this particular case, this was a very anomalous kind of situation, a very strange accident where the gas came out in a very strong and sudden when I use the word explosion, it's actually the expansion of the gas all of a sudden, and it caused suffocation and death for several villages. Coming back to thermal stratification in temperate and colder regions. So this is the same thing that you see. So this is a lake, the 3 layers, and the layer of the hypolimnion basically depends on, like I said, how deep can the light penetrate, because this is the dark and cold region. And you can see, because light is not penetrating, that means there's no heat, and you get a very sort of stable thermal profile. So temperature remains more or less constant throughout the year because of all these reasons. And you can see the fluctuation for the epilimnion. That is the top layer. So this top layer will show great fluctuations depending on the ambient temperature. So spring, summer, fall, as the ambient temperature changes, so will the temperature of the water through the seasons. This is the ocean, and you can see the ocean profile. So you have temperature profile in the top layer is uniform. You have the metalimnion or the thermocline, where that is by definition, the thermocline is the region where there is the steep fall in temperature. So that is defined as the thermocline. And like I said, I think I've observed it in a bucket of water. All you need to do is, this is winter time, fill a bucket of water with cold, normal water, not heated water. Take cold water in a bucket, let it be for a few minutes, put your arm in, and you should be able to feel, literally feel, the difference in temperature at the top and bottom. Water, the density and thermal gradient is formed immediately. So this is the thermocline, and then you can see the rest of the water column. So this is uniform. Then we have salinity. You can see a similar profile. I haven't talked about salinity, so I won't go into it. This is transmitted light. So assuming that the light at the top, in this case, is 88%, and as it, right, this is the maximum light is at the top, and as you go further down, it goes down. So that's the light profile. This is, I think there is a mistake over here. In terms of the labeling. Then you have oxygen. I've already explained the oxygen profile. The highest oxygen is at the bottom of the thermocline. So as long as there's mixing, you get uniform DO. And by definition, because of the thermal gradient, you will get the highest level at the bottom of the thermocline. And then as you go further down in the dark regions, you get utilization of DO by the bacteria, and therefore the DO concentration starts dropping. And the last one is suspended particle concentration. Now, suspended particle concentration is associated, you can say, with phytoplankton as well as other forces, other sources. And you can see that the euphotic zone, this is where the light is highest. So this is, yeah, there is some issue over here. Anyway, so this is where the light is highest, and you will get a large amount of algal growth, phytoplankton growth. And phytoplankton will contribute to the suspended particle concentration. So here is where you get the highest concentration. And remember that for the algae, they don't need oxygen. They are generators of oxygen. Who needs oxygen? Bacteria and the other organisms like fish and all the small organisms like insects and so on. So they are the ones that need oxygen. They are the ones that are depleting the oxygen. And the only source from in this layer, the hypolimnion, is diffusion from the top. So that's why you get very limited amount of oxygen in the bottom layer, and it gets depleted depending on the level of pollution. Okay, then we come to the next issue, and that is acid rain. And you might say that is an air pollution issue, not a water pollution issue. Well, like I said in the first class, all parts of the environment are related to each other. They are not isolated from each other. So whatever happens in the air is going to have an impact not just on water, but on soil and so many other parts of the environment. So we can't say that it does not have an impact. It has a major impact. We have a new issue called ocean acidification, even though it has a small change in pH, but it does have an impact. So all these sources of acids that are being emitted into the atmosphere, I'll just go into it. So here we have various things. Where is the acidity in rainwater coming from? There are several sources. So you have natural sources as well as anthropogenic sources. Now, you get emissions of volatile organic compounds. VOC stands for volatile organic carbon or compounds. And then you have nitrogen oxides. So X stands for, it can be 2, 3, or even 1, yes. So you have nitrous oxide, nitrogen dioxide, and so on. So these are NOx. Now, these emissions can come from the burning of fossil fuels, they can come from natural sources. So these are all being emitted into the atmosphere. And we also have from natural sources, we have SO2. So that again comes from burning of fossil fuels. So these are all, when they react with water vapor in the atmosphere, they are forming acids. So you have H2SO4, you have nitric acid, all of these are being formed in the atmosphere and they are contributing to acid rain. We also have a third source, and the third source is carbon dioxide. So now we already know, I think I mentioned in at some point, that carbon dioxide will react with water to form carbonic acid. Okay, so this H2CO3 is going to be formed when carbon dioxide dissolves in water or reacts with water. There are two things. One is dissolution of carbon dioxide in water, and then the second is the reaction with water. In all cases, and you all know, you've all had carbonated beverages, that is a simple example of CO2 dissolving in water and react. You can call it a reaction or dissolution, and that brings the pH down. So that is all contributing, all these sources, VOCs, SO2, NOx, and what is not shown over here is CO2, all of them contribute to the pH of rainwater. And if the pH of rainwater is less than what is called pure rainwater, which means 5.6, and we're going to go through the derivation of this in the next few slides. So, so this is all that happens. And so you have these gaseous pollutants in the atmosphere. They come down in two ways. So if they come down with water vapor, then that is called wet deposition. And if they come down without water, then it's called dry deposition. So these are the full, this is the full cycle, how these pollutants come back down to the earth. Okay. So from the earth into the atmosphere and then back on the earth. So, and this is a pH distribution map of rainwater over the US. You can see this on the eastern coast where the highest industrial activity is. So this is the area where you can see the pH level of rainwater is very, very low. So it's 4.3 all the way to 5.1, 5.3 and so on. And on the western side where the industrial activity is much less, it's closer to rainwater. And just remember that rainwater today is about 5.6. And I'll show you the derivation for why that is the case. What is the impact of acid rain? So the impact of acid rain first and foremost is on building materials. Now, if you have building materials that include limestone, marble, sandstone, metal, paints, which are metal-based paints, all of them will be degraded in the sense of weathering. Remember, acid dissolves even the hardest rocks. So the greater the acidity of any material, it will cause the dissolution of rocks, of metals, and any other material. So I'll just show you a couple of examples. So this is a sandstone sculpture in Germany, and the first photo is from 1908, and the second one is from 1968. This particular castle was built in 1702. I found this really dramatic, and industrialization in Germany was greatest during this period. So 1908 to 1968, when there was very little control on air pollution. And so you can see that in 200 years, from 1702 to 1908, this was the amount of erosion of the sculpture, not much. There's very little damage to the sculpture. And what happened in the next 60 years? You can see the difference. So this is the consequence of industrialization. And this is like this very dramatic example of that. And this is another example of natural erosion. So this is from a site that's very close to Kharagpur. So this is from Bhubaneswar. Just outside the city, there are Khandagiri and Udayagiri caves. They are sandstone caves, and they have exquisite carving on the stone. And there are two parts. So if you see this photo, there is one part which is completely protected. There is no direct contact of rainwater because of the nature of the carving. It's in a corner. And the other carved carving is completely exposed to rainwater. And this is 200, not 200, 2000 years. Okay, so these caves are estimated to have been carved about 1 to 2 BC. So that's about 2000 years more than that. And so this is about 2000 years, and you can see the level of erosion. There's almost zero erosion where there is complete protection from rainwater. And over here, you can see how much has eroded in 2000 years. So this is natural because I think this area has been relatively protected from industrialization. There's very little industrial activity on the eastern coast of India, and more so even in the Bhubaneswar region. It's only in recent decades that there has been some industrial activity, but more or less it's been very low. Throughout the ages, it's been very low. So let's take a look at some derivation for how does the acidity of rainwater, how can you calculate it, and what is the impact of increasing CO2 levels on the acidity of rainwater. So right here we have, I should have written the reactions. So you can write the reactions. Now we have H2CO3. This H2CO3 has a star on it. Now this H2CO3, like I said, with a star has two species, two chemical species. One is the actual carbonic acid, which is formed by H2CO3, that is formed by the reaction of CO2 in aqueous systems with water. So when the two react, CO2 reacts with water, it forms carbonic acid, and that is what we are looking at here. You also have dissolved carbon dioxide concentration. So there is some amount of CO2 which is not reacting with water, but it is in the aqueous solution. So the sum of the two is H2CO3 star. These are the equilibrium constants. So H2CO3 star will get deprotonated. The first deprotonation constant is Ka1. So you can write it as pKa. I think you're all familiar with the fact that pKa is written just like pH. So pH is the negative log of H plus and pKa is the negative log of K. Okay, so Ka1 and the negative log of Ka1 is 6.37. So that's the first equilibrium constant. The second equilibrium constant is the second deprotonation reaction. And when you look at the second deprotonation reaction, you get, in the first case, you get bicarbonate. In the second case, you get carbonate. So this Ka2 will give you a pKa2 of 10.33. Then we come to mass balance. So if I want to write the mass balance for carbon, this is CT. CT means total carbon. C actually stands for concentration, and CT applies to total concentration. So it's T stands for total and C stands for concentration. In our case, we are doing a mass balance for carbon. So we have three carbon species, H2CO3, HCO3 bicarbonate, and carbonate CO3 2-. This is our mass balance. We know the water constant, so we know the water equilibrium constant. So H plus times OH minus is equal to Kw 10 to the power minus 14. So pKw is 14. Okay. Now I want to solve for the pH. I want to know how much total carbon is there in the water because the carbon dioxide emissions are increasing. So as the carbon dioxide in the atmosphere increases, the amount of carbon dioxide that dissolves into water will also increase, right? So let us solve for that. Now, utilizing these equilibrium reactions, I can write H2CO3, bicarbonate and carbonate in this form as well. You can do it on your own. Just make sure you do it, because if you don't do it, you won't be able to understand where it's coming from. It's very simple. Each one of them has been derived from these equations. So if I want to write H2CO3, I can just bring Ka1 on this side and H2CO3 on the other side. And then I have to make, and okay, one more point over here, and that is I want equations in terms of constants and pH. I don't want any other variables because I want to solve for pH. So each one of these three species, these are our three unknown species, each of them has to be written in the form of pH and the equilibrium constants. And that is what has been done over here. I'll come back to this point in a little bit. Now, there are two types of systems. If you think about your carbonated beverages, it's a closed system. So when the people who manufacture these carbonated beverages, they add CO2 under pressure into the aqueous solution and then they bottle it or can it. And when you open it, the CO2 comes out in a rush, right? If you happen to shake it and so on. So those are closed systems. The amount of total carbon in that system is known, and you know from tasting it that the pH is very low. If you test it, it's anywhere between 2 to 4. So it's extremely low pH. So this is the distribution of the carbonate species under different pH conditions. So as the pH goes down, H2CO3 star is the dominant species. As the pH comes to 7, 7 is what we like, and 7 is going to be dominated by bicarbonate. And if you go into the alkaline region, then carbonate starts dominating. Okay, that's the closed system. That's not what we are interested in. That's good for drinking carbonated beverages, but that doesn't tell us anything about the atmosphere. So here is the atmosphere. The atmosphere is water in equilibrium with the atmosphere is an open system. So you have water at the bottom, atmosphere on top, CO2 levels in the atmosphere are rising. So you know your Henry's constant, and you know that Kh is the ratio of the partial pressure of CO2 in the atmosphere divided by divided by H2CO3 star. It's the star that is very important. That star represents two species, not a single species. And that is something to keep in mind. And when you go through this solution, you will be able to understand how it happens. So the mass balance remains the same. Our mass balance is still the same. We have the same three species. So H2CO3 star, bicarbonate and carbonate, they are all together. So the same three. The only difference now is that CT is not, see the carbonated beverages, just imagine those. Over there, the total amount of carbon is known. They know how much carbon they are adding into the system, right? So there it's defined. CT is predefined. But in the atmosphere, CT is not predefined. So here, CT has to be calculated. And so that again, yes, this is where right. So here we have log concentration versus pH, and you can see that CT changes as a function of pH. Why does CT change as a function of pH? Because of this phenomenon that you have different species forming as a function of pH, and because you get greater dissolution at the lower pHs, you get oops, yeah. So one second, let me get that. Okay, yeah. So what happens is that in an open system, what is fixed? In an open system, it's Henry's law that governs what is governs the total amount of carbon in the system. So it is this equilibrium between the gaseous phase and the aqueous phase that will determine how much is there in the water. And you can see H2CO3 in this case is constant no matter what the pH is. And that is because this is our governing equation. So our KH value, which is a function of the partial pressure of CO2 divided by H2CO3. So this becomes the governing equation. And this is our 10 to the power minus 5 in this case. And let's see what else. So let's come back to our mass balance. Now, in the first case, in the closed system, CT was fixed and these three were variables. In our open system, H2CO3 star is fixed and the remaining three are variables. Okay, and they are varying with pH. And you can solve it for any different pH, you can solve it and satisfy yourself that yes, they are varying. So as the pH goes up, the total amount of carbon in the system is also increasing. And I think that's because you get more and more CO2. That's correct. So you get more and CO2, no, CO3, 2 minus, more and more carbonates are forming. So the reactions are shifting towards carbonate and you get more bicarbonate, more carbonate formation. And that's what you see as the CT curve. So this is your open system. Now, why am I going through all this? The second question, like I said, the main question we're trying to answer over here is that if CO2 emissions continue to increase, what is the impact on acid rain? Not just acid rain, what is the impact on pure rainwater? And what is the impact on surface water bodies, including oceans? So I've taken this directly from the book, and what is shown over here is an example of how you can calculate the pH of clean rainwater that is in equilibrium with atmospheric CO2. Now the atmospheric CO2 that they have assumed is 300 and let me see whether that's, one second. Yeah, I think they've assumed 350 ppm, and we know that our current levels are far above 400 ppm. Okay, so let's solve for 400 ppm. So if I say the partial pressure of CO2, what is it for 400 ppm? You can convert it. ppm is parts per million. So if my atmospheric pressure is 1 atmosphere, that 1 atmosphere is occupied by 400 ppm of CO2. So 400 times 10 to the power minus 6, it's parts per million. So 10 to the power minus 6. So 4 times 10 to the power minus 4, and you can convert it and write it in this form that it is 10 to the power minus 3.4 atmosphere. Okay, so this is our PCO2 for 400 ppm. If today's concentration is 420, you can recalculate for that. Then we come to the next point. So in the previous example, I showed you mass balance. There is another equation that you can use, and that is the charge balance. And the charge balance means that all the positive charges, the sum of the positive charges has to be equal in concentration to the sum of the negative charges. So all the protons on one side, there is nothing else that is positively charged, so it's just protons. So all the protons on one side of the equation, and you have the hydroxides, bicarbonates, and carbonates. The 2 is missing over here, so it's 2 times. It should be 2 times CO3, 2 minus, because it's a charge balance, not a mass balance. So that's missing. And since this is an open system, like I said, you use Henry's law, and Henry's constant is related only to temperature. We've already seen the independent expressions for the three carbon species. So you have H2CO3 star, HCO3 minus, and CO3 2 minus. You can substitute in this charge balance equation in terms of the equilibrium constants, and the only unknown that should remain in your final equation is H plus. And then what you will find is that it's a cubic equation. So when you get this form, when you try to solve it, it's a cubic equation. There are two ways of doing it. If you know how to solve a cubic equation, do it that way. Otherwise, you can use a spreadsheet and trial and error to converge on a solution, and that's what is shown over here. So you'd have convergence. You know how to do convergence, where you you assume a value, you assume an initial value for the pH. For every pH value, you come up with a solution on the left-hand side as well as the right-hand side. When the two start converging, you start coming when the two values on left-hand side and right-hand side start coming closer with different assumptions, you know that in this case, the least error is where you have your answer. So you want to minimize the error, and as long as it's less than, in this case, 1%, uh, yeah, it's far less than 1%, yes. And that's the solution. So it's 5.6 for 350 ppm. How much difference will it make if the concentration is 400 ppm and then let's say 500 ppm? How much pH decrease will happen? And what is the consequence of decreasing pH? So here is the consequence of decreasing pH. Some of the aquatic species will survive. So something like frogs, they are considered resistant species. So even if the pH goes down to 4, no problem, they'll continue to survive. But what are the other species going to do? Many of the other species will not be able to survive under acidic conditions. So you have the more sensitive. Trout is considered to be a fairly sensitive species, and it can tolerate up to, let's say, 5. Bass can tolerate up to 5.5, perch more resistant, salamanders just about that. Then you have shellfish, clams, snails, crayfish, all of them have levels of tolerance that are lower than the frogs. So different species will start dominating as the acidic level in water changes. I can show you some more examples of fish in different types of lakes. Now, when you go to a lake or a reservoir the next time, just look at the rocky areas that create that lake or reservoir. Okay, they're always surrounded by rocks, and even the bed on which the water is, even that's literally called bedrock. Okay, so these lakes are, if the surrounding rocks, including the bedrock, has fair amounts of carbonates in it, then the lakes are buffered by these carbonates. And therefore, when you have high levels of carbon dioxide in the atmosphere, it will remain in equilibrium up to a certain point. As long as that buffering by carbonates exists, that will continue to exist. Okay, so the the pH water, let me rephrase that. The pH of the lake water will remain stable. But once that buffering capacity is exhausted, then again the pH will drop. So I'll come to that in a little bit. And if the surrounding rocks have a fair amount of limestone, limestone is a carbonate rock. So these are what are called calcareous lakes. They have high amounts of calcium and carbonate, so they remain in equilibrium. They are well buffered. And in general, they are not affected by acidic rainwater. So as long as there is a source of bicarbonate, the lake remains fine. But what happens in other lakes? So if you have a bicarbonate lake, as long as the rocks have a significant amounts of carbonate, they will dissolve and the pH will be greater than 6.3. Now, if there is lack of bicarbonate and carbonate, then we call them transition lakes and the pH ranges from 5 to 6. If the pH falls below 5, it's called an acidic lake. And the consequences for the fish population are enormous. So here we have bicarbonate buffering. So you can see the pH and the proton concentration. As it is added, the bicarbonate lakes will resist pH change. So you can see it's above, it's between 7 and 8 and it remains steady. But in the transition lakes, the pH drops very rapidly and in the acidic lakes, you again see acidic conditions and a decrease in the pH. So this is just the bicarbonate concentration as a function of pH. It's the same as the line shown over here. You can see it, yeah, in this part of the curve. This part of the curve. Yeah. Last point is about these lakes and the fish population. So somebody must have done a survey of Norwegian lakes. You know that Norway is in the temperate and frigid zone. So that is where these are countries and aquatic and ecosystems that are extremely sensitive to changes in pH and temperature. Okay, so that is something that you can see very clearly over here. So look at the number of lakes. It's also a lake-based kind of country, and you can see the number of lakes. So 684 lakes were surveyed, and out of them, 129 were bicarbonate lakes. So there was sufficient buffering of the pH, and you can see that the fish population in most of the lakes. So so there was a good amount of fish population in more than 50% of the lakes, and the remaining, let's say 40% were distributed in 0, 1, and 3 categories. There may be other factors. Then as the pH goes down, you can see the number of lakes with transition or acidity in the lake water are much higher. And you can see the fish population going from, it's dominated by sparse fish population to 0 fish population. So you can see the impact of acidity or pH drop on the fish population in these lakes. So like I said, lakes are vulnerable to acidification, partly from this can be because of acid rain. It can also be because of wastewater discharges. So in our country, we have wastewaters being discharged with or without treatment. And if the treatment level is not adequate, then you're contributing to the acidity of the water. So that is also going to contribute to the acidity of lakes in our type of environmental conditions. Okay, so we have areas which have shallow soil layers, low permeability. Those kinds of lakes are highly vulnerable to acidification. If you have granitic bedrock, if you have a steep watershed, so the water is coming down rapidly from the watershed area into the lakes, all these are, so there's very little buffering of the acidic rainwater. And if you have evergreens like coniferous plants and trees, that will also result in acidification. That brings me to the end of this topic. I can take some questions for about 5 minutes, and then we will take a break and then start the next topic. No questions. Everyone has understood everything. Is that right?
Ma'am, how can evergreen conifers make lakes vulnerable to acidification?
My guess is that they contribute some level of acidity to the water. They are also contributing to some level of acids. There are other vegetation that also contribute acids, but that is after decomposition. So I think there is something that is more obvious about coniferous trees and plants. Yeah. All vegetation, when it decomposes, it creates acids. In fact, all organic matter. Okay, when organic matter decomposes, it generates acids, and then those acids are converted to CO2 and water. And you know that CO2 and water itself is carbonic acid. So that is one set of reactions, but that applies to all organic matter, whether it's of animal origin, vegetable origin, it doesn't matter. It applies as a general rule. So the only difference between all the other organic matter and coniferous organic matter, I think, is that coniferous trees have more acidity compared to the other plants. That's my guess. Yeah.
Okay, ma'am. Thank you.
If you don't want to ask a question, you can write it in the chat box. Nothing? All right, then we will have to start the next topic. I will close this. You can all take a 2-minute break and I will set up the next one. So we'll start in 2 minutes. Are you able to see the slides?
Yes, ma'am.
Okay. So we're going to start with the next topic, and just remember that this topic is not going to be on the test on 7th, and it will be on the next test. Okay. So let's get started.
Ma'am, could you repeat please what you were saying?
I'm starting a new topic, and that is water treatment. So we have two more related topics to water pollution. The first one is water treatment, and the second one is wastewater treatment. And these two topics, I am starting it today, but it's not on the test. We have a test on 7th from 3 to 4, and this topic is not on the test. Everything up to the previous point is on the test. Okay.
Okay, ma'am.
So let's come to why should I treat water? Why do people treat water before drinking? And the first thing that we need to know, and we probably already know that, is that we all want safe and clean drinking water. That is our goal at an individual level, at the society level, at the national level. It doesn't matter which level you're thinking about. Everyone wants and has a right to safe and clean drinking water. That's one of the sustainable development goals as well. So, if that is my goal, how do I achieve it? The first thing I need to do is I need to identify a source water. So, I can, whether I'm in a village or whether I'm in a city or whether I'm planning a new city, whether it's an old city, whatever it is, I have to identify the source of water not just for my present requirements, but I need to account for my requirements and not at the individual level. Let's say we are planning for a city or a town or a village or even at the national level, okay? It can be at any level. That's an important point for anyone to remember, that I may be building a house and I'm thinking about myself and my family, or I may be looking at, I may be a planner looking at a town or a city, or even at the national or state level. Okay, anything is possible. So, in any case, you have to think about all these factors. So, you have to think about the identify. First thing you need to do is identify the source water. Now, it's not enough to identify the source water for your current needs. You want to look at 10 years from now, 20 years from now, whatever is the design period of your system. It can be as much as 50 years or even longer. So, you need to identify your source water. You need to ask yourself, is this particular source, whether it's a shallow well, whether it's river water, lake water, deep tube well, these are the normal common sources of water. Is this water source going to be adequate for the next 10 years, 20 years, 50 years, and so on? Okay. So, will it give me the required quantity? Will it give me the required quality? If the quality is not up to the mark, what should I do? What is the cost of treatment? So, we'll come to that later. So, the first thing we need to do is identify the source, how much quantity is there, and what is the level of the water quality. How far is it from my requirement? So let us say you think about campus and you say that the river is about 5 kilometers away from campus. That is one possible source. And within campus, you can always put in a tube well. You can put in tens of tube wells, and those tube wells are within the campus. So that is the location. Now, the river is, at least the river that we have, River Kasai or Kansavati, it is, I think it's a perennial river, but maybe it runs, yes, I think it has high flows and low flows, but it does have adequate quantity. Now, if the future population is going to be very high, then obviously that quantity may not be sufficient in the low flow periods. So in that case, you need to augment that source with groundwater, and so you have bore wells. So in campus, what we have is a mix of river water and groundwater. And you can have in today's conditions, in the current scenario, most cities, towns, everywhere you see, people are looking for groundwater. Groundwater has become the preferred water source wherever people have the ability to tap into the subsurface. Okay, and then we come to cost and sustainability. What is the cost of supplying water? Is the water, once you answer the first 3 points, then comes the cost associated with it. Now, before we had the technology for boring wells, it was easier to put a pump and pipelines into a river and then pump the water to the location that you need to serve. But with the cost of boring a well going down, it's a very, very cheap process now. So that's why people are going for groundwater in a big way. That brings us to the next question of sustainability. Is it sustainable to use groundwater in such a big way? And in certain areas, the answer is yes, and in other areas, the answer is no. So sometimes, for example, I come from Gujarat, and Gujarat is a water scarce region. So Rajasthan, Gujarat, Andhra Pradesh, Telangana, all these areas are relatively water scarce. Maharashtra, all these states have water scarcity in a big, there are very frequent droughts. The rain doesn't come in those years, and when there is a drought, people go for deeper and deeper tube wells. So the cost of getting water increases, and the sustainability of using groundwater also becomes somewhat questionable, because one, it's financially unsustainable for many people, especially poor villagers and all. So then they have to rely on other methods. That is one issue. And the second is, what if the well runs dry? So when the well runs dry, you have nothing left. You have emptied the entire source. So it becomes highly unsustainable. So you need a lot of planning to uh, do this kind of water management. So that's our first set of issues. Then we come to the second set of issues. Now, let's say I have a river, a lake, or a reservoir, which is the water resource for that particular location. What am I doing to protect it from contamination? In India, we normally, in general, I don't see what is called source water protection. In other countries, in developed countries, you often see what are called source water protection programs. So they create a buffer zone, they create a green zone around the source water. Let's say you have a lake, they create a green zone or a buffer zone in which no activity is allowed. So no commercial activity, no residential areas, no industrial activity, nothing is allowed. It is just like an eco reserve. So when we have our conservation activities, when we have our eco reserves or these conservation reserves, it is just like that. So the watershed is maintained in that level of natural conditions are maintained, so that the watershed does not get polluted water from commercial, residential, and industrial sources. So these are called watershed management plans. And you have to have a watershed management plan to ensure that whether it's a surface water or any other source of water, that the water will remain free from contamination in the future. So that's a very important point for our country. Then we come to appropriate level of treatment. So we have standards. So we have drinking water standards, which tell us that these standards have to be met. And if the source water in its natural state is not meeting those standards, then we have to provide treatment. Okay. So appropriate treatment of the raw water or the source water is essential. And finally, we come to safe distribution. Now, let us say I do everything correctly. I identify all these 3 points. Let's say I've taken care of the first 3 points. Then I am storing this treated water and distributing it to the service area. We call the area that we are providing this water to, that is called the service area. So this water is then distributed to the service area through pipes and so we have the main pipelines and we have the branches of those main pipelines. So that is where the distribution system is. And you can have underground reservoirs, you can have elevated reservoirs, you can have above ground reservoirs. All three are possible, and under different conditions you will have different types of reservoirs. This is the water that you get at the tap. Now your water at the tap should be clean and safe for drinking directly. Most of us know that our water at the tap is neither clean nor safe for drinking directly. We all have what is called point of use treatment. So point of use treatment means we are unhappy with the quality of water that is being distributed, and we have additional treatment at the point, which means at the tap. So that's very common everywhere in the world today. Okay. Then we come to what is called conventional drinking water treatment. Now, there are two levels of treatment. One is conventional and the other is either you can say non-conventional or advanced drinking water treatment. So for the purposes of this class, I'm just going to focus on conventional drinking water treatment. Advanced topics, we don't have the time to cover them. So you can ask me questions specifically, but other than that, we're not going to do anything with that. So we come to our primary objective in drinking water treatment. Like I said, our main objective is to provide safe and clean water. Why is safe and clean water essential? The first thing is it's a health issue. If my water quality is not good, so what? We all know, even as little kids, one of the first things we learn is that the water we should make sure that the water we drink is clean, right? And most of us learn that if it looks a little bit muddy, the clear water is better than the muddy water. So as a general thumb rule, that is appropriate. Now, what are the health concerns? So if you have slightly muddy water, what is the consequence? There are two issues that I have noted at the top. One is microbial pathogens and the second is particles. So muddiness comes from these particles. They give it color and turbidity. And these pathogens, even though they are capable of being without attachment to the particles, they tend to like being attached to particles. So this muddy water is likely to have higher concentrations of these pathogens compared to let's say a water without the particles. Okay, so in either case, it's a health issue. And anytime you go outside and drink water and within 24 hours, if you've ever experienced a stomach upset, you know that it's probably the pathogens in the water or in the food that you may have had in the last 24 hours. So these are just common occurrences that happen quite frequently anywhere. So health concerns are, like I said, a major motivation or a major reason for wanting to remove microbial pathogens as well as particles. And the other issue is aesthetic. If I give you two glasses of water, one is muddy and the other is clear, you will go for the clear water. That's an aesthetic choice. Very clearly, you want to know, you want clean, and because we are all, even an uneducated person knows that clean and clear water means it should be clear. It should not be muddy. And the reason is because these two generally very often go together. It's like soil. If you happen to play with soil, you're generally told to wash your hands before you eat or drink anything, right? And that's because soil is also teeming with microbial organisms, and some of them may be pathogenic. Not all, most of them are non-pathogenic, but if you happen to come in contact with a pathogenic, why is soil a reservoir? Why is water a reservoir? Because fecal matter from animals, from birds, from human beings is all going into the water and soil. And so it comes into whatever we do, and that's why it becomes an important issue. Then we come to total dissolved solids. Now, another issue that you may have noticed, depending on your location, sometimes when you wash your hands, there's no froth or foam, right? So why does that happen? Why is it that under certain conditions, the soap does not work? And we often say this soap is not working, it's not a good soap, but it's not the soap's fault. The fault lies in the water. The water contains what we call hardness causing minerals, and these are calcium and magnesium. So hard waters are the ones which have more calcium and more magnesium, and because of the presence of these, sometimes with these waters you can actually observe it happen. If you soap your hands and the water is hard, you get these white crystals. You get this curd-like material. It looks like curd. And these are crystals that are formed because of the hard water, because of calcium and magnesium in the water. So it's, again, I should say it's not entirely aesthetic. It's actually, there are issues related to the aesthetics. Yes, that's the aesthetic part is there. It's also a health issue to some extent because no one likes very hard water. If you have very hard water, let's say something with more than 500 milligrams per liter of total dissolved solids, then what will happen is that one, you won't like the taste. It tastes saline, so most people will reject it on that basis. That is the first thing. The second thing is you will get precipitation of calcium and magnesium when the concentration is high. And again, that becomes partly aesthetic issue. And then there are many other issues like the inefficiency of heating appliances. I've already mentioned the soap problem. So all these things, so your detergents won't work, your soap won't work, and it's not the fault of the detergent or the soap, it's the fault of the water. Okay, so you have to remove these two, calcium and magnesium need to be removed, and we will go through all that. Besides these two, so like I said, if you're dealing with surface water, the first two are the major problem. If you're dealing with groundwater, and like I said, more and more people are moving towards groundwater, groundwater tends to be harder. I'm making a very broad generalization. Groundwater tends to be harder more often than surface water. Not that you can't have exceptions, you can have exceptions. But if you're using deep groundwater, then hardness is very frequently an issue, and that becomes the main point of concern and treatment. Okay, so these are the primary objectives. Then we come to the secondary objectives. Secondary objectives are removal of other pollutants that are present in water. So I've already mentioned that if you have hard water, the taste goes bad. So most people will reject it simply on that basis. So that is one criterion that needs to be. Most people will immediately reject water that has a taste, whether it's a salty taste, acidic taste, soapy taste. All these kinds of things will be sufficient reason for rejecting a particular water. And then more than that, I myself have experienced it. Let's say you buy bottled water. The moment you open the cap, though you open the seal, you get this odor, and that odor is a very peculiar odor which is associated with organic matter growing inside. Let me put it another way: with organic matter present in the water, and bacteria may be growing on it. So it's what we call a musty odor. So it's, I don't know how to describe musty, but most of you have probably seen it either in bottled water or sometimes lakes. If you go to lakes and they're not very clean water, you will find that there is a certain musty odor. And that odor again is sufficient reason for rejecting it. pH is, like I said, if it's acidic, you will reject it. If it's highly basic, you will reject it. So these are basic ones. And then you have both inorganic as well as organic pollutants. So if you have inorganic pollutants, hardness, which is related to calcium and magnesium, that is to be examined. And we have methods. We have lab methods and analytical methods that can be used for determining the concentration of all these different compounds. Alkalinity can be associated with hydroxide or with bicarbonate. So you can measure it in the lab. And like I said, that is also an important parameter because that provides the buffering capacity of the water. Then you have iron, chloride, fluoride, copper, manganese, sulfate, nitrate, mercury. Now let me highlight a couple of them. So we have mercury, cadmium, selenium, arsenic, and chromium. These are, and lead. These are considered toxic heavy metals. They have no useful properties. They should not be there in water. Their levels should be zero. So these are completely toxic at even the lowest concentration. Then you have other examples. You have iron, copper, manganese, aluminum, boron, radio, and that's it. These are the other metals which are good at low concentration. So when you talk about mineral water, many people say, oh, mineral water is good for your health, right? So these are the things that may be present in mineral water, and because they are what are called micronutrients, they're considered to be good for the health, and therefore people like them. But again, the point to keep in mind is that if the concentration goes too high, then the same metal which is useful can become toxic. Okay, so there are issues either way with these other metals, but the toxic six, you can call them toxic six. So the toxic six are mercury, cadmium, selenium, arsenic, lead, and chromium. Okay. Okay, and all the others are micronutrients. And then we have radioactive material. So supposing you live in an area where there is the possibility of radioactive materials being present in water exists. So then that also becomes an issue. We chlorinate water. Now, too much chlorine in water can also be a problem. So that is residual free chlorine. We will be spending some time on that. And total dissolved solids. So total dissolved solids is TDS. And we measure it in the form of electrical conductivity. And that is what we will, I think we will spend some time on it. Yeah. So those of you who have heard about saline water or desalination plants, they're all related to total dissolved solids removal. Then let's come to organic pollutants. Organic pollutants can be natural in origin. So you have natural organic matter. It is organic matter that is of natural origin. And when I was talking to you about musty odor, it often comes from natural organic matter. So let's say somebody picked up water from an area and didn't treat it, bottled it and sold it. So that's where you get your musty odor. Okay, that's very common in bottled water. Then we come to pesticides. Pesticides are synthetic organic compounds. So SOC or pesticides are another example. Oil, PAHs. PAHs stand for polycyclic aromatic hydrocarbons, and they come from, again, both natural as well as anthropogenic sources. Then you have anionic detergents and phenols. So these are some of them are of both. So these are of both natural as well as anthropogenic origin. Detergents and phenols are generally anthropogenic, but phenols may be, to some extent, there may be some natural phenols, yes. Okay. Any questions at this point? Otherwise, I'll just go on and on. Okay, so like I said, there are two major types of water sources. One is groundwater and the other is surface water. So what are the examples of surface water? We have lakes, reservoirs, ponds, and rivers and streams. So those are all surface water bodies. So within surface water bodies, we will have flowing surface water bodies and standing water bodies. So lakes and reservoirs are standing water bodies and rivers and streams are flowing water bodies. And groundwater we can categorize into two parts. We can say shallow groundwater. So if you have ever seen a hand pump, villagers or small towns, even people have these hand pumps, or you can see open wells in villages. And what you see is that people are pumping water from shallow depth. So you can go up to about 40 meters, they tell me. So 40 meters is what you can do with shallow um, wells. And then you have deep tube wells. So if you want to go deeper than that, you have to have a tube well. And these tube wells can go up to 150 meters or maybe even more. Now, you do realize that groundwater is found below the subsurface, and because it's below the subsurface, it is not in equilibrium with the atmosphere or with atmospheric oxygen. So, because of that, the dissolved oxygen level will be less than surface water. So we've already seen how dissolved oxygen levels in surface water changes for various reasons. Now, groundwater, because it's not in equilibrium, it has a lower level because of that, not necessarily because of pollution. Even unpolluted groundwater is likely to have less dissolved oxygen compared to surface water. That's point number one. Second point is microbial contamination. Now, if the groundwater is very deep, the water that goes into the ground is being naturally filtered as it moves in the subsurface. Because of the natural filtration, very little microbial contamination of groundwater happens. So, so the deeper the groundwater, the lower the microbial concentration. I've already mentioned to you that soil is generally contaminated with fecal matter from all kinds of sources, birds, animals, humans, and so on. So all that material will naturally flow further down, but as it goes further, as the water carries it further down, it gets attenuated. So it basically becomes less and less because there's a longer distance for the water to travel and carry microbes with it, and the filtration through the subsurface is more and more obvious, right? So that is another advantage with groundwater. So it's good quality water. The only thing is dissolved oxygen is less. Then we come to higher concentrations of inorganic compounds. So inorganic compounds or ions, let's take a look at the inorganic ones, anions and cations. Anions are chloride, carbonate, sulfate, sulfide. If it is reducing condition, so if it is completely anoxic, let's say the dissolved oxygen goes to zero, if it's very deep groundwater. So if the water is very deep in the ground, it's completely out of contact with dissolved oxygen, you won't have sulfates, you'll have sulfides. Then you will have other minerals. You'll have bromide, nitrate, fluoride, arsenite, arsenate. All these can be found in groundwater. You can have cations, calcium, magnesium, iron, manganese, aluminum, arsenic. All these are often present in groundwater in significantly high concentrations. So hardness, like I said, is the concentration, the sum of the concentration of calcium and magnesium. Now, surface water, on the other hand, there's no natural filtration. Whatever is in the surface runoff goes into the surface water, right? So because of that, you can have very high turbidity and microbial concentration. Because what is surface runoff? Surface runoff is the sum total of water flowing over soil, over built up area. It can be open, barren land, it can be green land, it can be forest, it can be anything, right? All of that will result in high turbidity and high microbial concentrations. And the dissolved oxygen level, we have already seen that in the previous topic. The dissolved oxygen concentration will depend on the organic matter concentration. Now, if it is natural organic matter, the dissolved oxygen will not be depleted very quickly. But if it is wastewater discharges, which is the case in most rivers and streams or even lakes, then the dissolved oxygen concentration will get depleted very rapidly, especially with municipal sewage, because that organic matter is highly biodegradable. So the dissolved oxygen gets depleted very quickly. So I've said all this, and let me see if I have missed anything. Now, what you see over here in this slide is differences between deep groundwater and surface water. So surface water and shallow groundwater, because shallow groundwater is getting shallow groundwater, the water comes from surface water or from rainwater. So very often, those of you who live in villages, I'm going to ask you this question in a few minutes. Let's see. So let's take a look at deep groundwater. So deep groundwater is not influenced by surface water, and shallow groundwater is either influenced by surface water or is influenced by rainwater. So those are the so that is one group. So like I said, dissolved oxygen in deep groundwater is much lower than surface water or shallow groundwater. Because if you're comparing, let's say, shallow groundwater with surface water, you'll find there's very little difference because they're more or less very close to each other, okay? Literally very close to the surface. And I can tell you that here in Kharagpur, I've noticed it that during the monsoon, the groundwater table often comes above the land surface. So if you have depressed land areas, then the water table rises above the land area, the land level. So that is, this is a water-rich region, and in water-scarce region, you will never see a phenomenon like this, like that. Um, So you have gases, like I said, as the DO level goes down, you will get a buildup of gases like carbon dioxide and hydrogen sulfide. You get what are called reducing conditions, because of which you will get iron in 2+ form. You will get manganese in 2+ form. You will get arsenic in 3+ form. Yes, that's correct. So these are some of the other things that will be, and this never happens in surface water, which is well aerated. So if you have good amount of DO in the surface water, these gases won't be there in any significant amount. They will be removed before they're formed, depending on oxygen levels. Then we come to microbes. Now, I already said if it's deep groundwater, the microbes will not get to it. And in surface water, they are all the time, they are there in millions and billions of cells per ml. Okay, it depends on how much impact of wastewater there is. Then you come to turbidity. Turbidity is that muddy look in the water. So again, because of filtration, deep groundwater will have less turbidity compared to surface water. These are very broad generalizations. And like I keep repeating this, there will be significant exceptions from one case to another. So yeah. So then you have cations. Generally, because groundwater is in contact with rocky material. So the aquifer material where the groundwater is found, that is intimately in contact with the aquifer solids. And these aquifer solids are basically rock, broken down rock. Okay, so these are dissolved elements. So you get a large number of dissolved elements, calcium, magnesium, manganese, iron, the list goes on and on. Okay, so these concentrations will be very high in groundwater compared to surface water. They will precipitate because when you bring something, let's say you bring deep groundwater to the surface, what will happen is if the DO level is very low, close to zero, many of these compounds like iron and manganese will be in dissolved form and reduced form. So Fe2 plus and Mn2 plus. You bring it to the surface, they will come in contact with oxygen from the air and they will get oxidized. So this Fe2 plus will become Fe3 plus, Mn2 plus will become Mn4 plus. So this is where you get um, removal, and that's what happens in surface water. So they will precipitate. So Fe3 plus and Mn4 plus, they are very insoluble. So they will precipitate and they will settle down. So your dissolved concentrations will be much lower. Then we come to total dissolved solids. Total dissolved solids are generally higher again for the same reasons. All this together is total dissolved solid. So it's generally higher and lower for surface water. Flow velocity in groundwater is very, very low. Orders of magnitude lower than surface water. And because the velocity is much lower, the residence time is much, much greater. So you may get residence times of the water maybe more than 100 years, it may be 10 years, 100 years, whatever. And the problem with that is that if you pollute groundwater, the consequences are very long term. Okay, so if I pollute the groundwater that I am dependent on today, the consequence will be for me and for maybe 2 or 3 generations or even more. We looked at the self-purification capacity of a river and we saw that the DO level will come back to normal after a given amount of time. So within a limit, this is okay for surface water as long as we do not exceed the self-purification capacity of the river. But a groundwater has no self-purification capacity, zero. There is no, because it's not in contact with the atmosphere. There is no way for the groundwater to purify itself. It's just not going to happen. So you have to have remediation, treatment. It's difficult, it's expensive, and it's, like I said, it's invisible, so it's very difficult to do. And in the case of surface water, water treatment has been going on for almost 100 years, maybe more, and it's not so difficult or expensive in comparison to groundwater. Okay, I am going to stop over here. I want to ask you a few questions. I want to do a little survey, which I usually do when I have a physical class. So first thing I want to know is how many of you are currently living in villages? Please raise your hands. Keep going, keep going. That's all? Okay. 6, okay. Good. I want to ask the 6 of you, what is the source of your drinking water? We'll start with the first one, Sneh Singh, Sneh Bandhu Singh.
Ma'am, the hand pumps are
Louder, please, louder.
hand pumps, the groundwater
Okay,
shelf.
so groundwater, hand pumps, and that is making it a shallow groundwater source. Okay,
Yes.
right. Okay, before I go to the next one, Sneh Bandhu Singh, where are you from? What is the name of the village? Which state?
Actually, village name is Rohua, town Balia, Uttar Pradesh.
Okay, right. So hand pump. Okay. Next one is Jai Prakash.
Yeah, hand pump.
Hand pump. Where are you
Yeah.
located?
Bhagalpur district of Bihar.
Did you say Bhagalpur?
Yes, yes, ma'am.
Okay. All right. And Lakshya.
Rainwater harvesting, ma'am.
Rainwater harvesting. How is the water treated?
Um, we use the RO filter as well after collecting the water. Means before drinking, we treat it with the activated charcoal RO.
Excellent. And this is your personal at the household level or the municipal level?
No,
Who
it
is
is at my household level.
household level? Right. Okay, good. That's very good. Where did you say you are from?
I am from Jetaran, Pali district, Rajasthan.
Okay, okay, very good. Next one, Turre Sai Krishna, Girish.
Um, Ma'am, from Wells, ma'am.
From hand pumps or open
Yes,
wells?
ma'am. Open
Which one?
wells, ma'am. We have water purifiers, ma'am.
Okay, and so somebody has to draw the water from the well?
No, no, ma'am. Hand pumps.
Hand pump. Okay, right. And what is the location?
Visakhapatnam district, Paderu, ma'am.
Okay, very good. And is there any treatment of this water prior to drinking? So one said rainwater harvesting, so there's treated water over there. What about the rest of you who are using hand pump water?
Actually, ma'am, here the water is like good for drinking, fit for
It's,
drinking purpose.
so how often do you have to pump the water?
Like, ma'am, for all purposes, we pump the water.
So anytime you need water, just like a tap, you go to the pump and you pump the water, right?
Yes, ma'am.
Okay, okay. That's very good. There was a sixth person. Somebody left. Who is the person who left? Okay, you don't want to tell us where you're right.
No, ma'am, it was me. I raised my hand by mistake. I pressed the button by mistake.
Okay, all right. Now, what I also want all of you to think about is what is the, so for those who are not from villages, I want all of you to identify the water source that you have, and don't tell me that it's the overhead tank. That's not a sufficient answer, even though that may be the most obvious answer. You should know, let's say you're living in Kolkata, you may have to find out where your water is coming from. So for example, like I said, in the campus we are using both river water as well as groundwater. So some of the hostels have groundwater and some of the hostels have river water, right? So I would like all of you do this without worrying about your grade, and you can those of you who have any interest, you can post your answers. You can say, I am from so and so city, and this is my source of water. Is that okay?
Okay, ma'am.
Yeah, okay. So that is one of the main things. And do you have any questions? So we have just enough time for me to deal with any other questions. So let me know. No questions? Okay, right then. All right, that's done then. No issues, no questions. All right, right. So we will meet again on 7th from 3 to 4. Okay.